So this is the communication system syllabus. So again, this one I have taken it from the Gate official website, and this is bit lengthy syllabus as compared to the signal and system. So here we will start with the analog communication topic, which include the amplitude modulation and the angle modulation. And then we will go to the digital communication, which has a lot of other topic included like PCM, DPCM, and all the key like amplitude shift key, phase shift key, and frequency shift key. And then all this different kind of like cottage amplitude modulation. This is like a kind of decoding method to minimize the error and all. So all this topic we'll go through one by one. And then we have a random process and random variable. And the last topic is information theory encoding. So we will start with the analog communication. So this is the typical communication system architecture. So in this you will see a transmitter and the receiver. Okay, and then we have a channel in between the transmitter and receiver. The channel can be something like wired, like twisted pair, or it can be wireless, and it can be like some coaxial cable and so on. Okay. So this channel can be any medium which we use to transmit the signal, and receiver will receive the signal through this channel. Okay. Now before the transmitter, the signal that we have, the input message might not be in the form of electrical. It may be some kind of mechanical signal, or it can be audio signal, which we want to first transform into electrical signal, and then we will apply it to the transmitter to transmit it. Okay. So in between the message and the input electrical signal, there is a circuit called transducer, which converts the non-electrical signal into the electrical signal. And once we have electrical signal, there will be transmitter which has some kind of block here, which take this input signal and transmit it through the antenna or maybe some wired. So if it is antenna, it will transmit through the wireless, and if it is wired, it will go through maybe some twisted pair or coaxial cable. Okay. Then once we transmit it to the channel, the receiver will receive the signal from the channel and do some processing here. Okay. And then after the processing, we'll get the output signal, and we want this output signal to be almost same as the input signal. Okay. And then from this output signal, we will do the opposite operation that we have done at the transmitter side. So here we have a transducer which converts the non-electrical to electrical. Here we have a transducer which converts the electrical to non-electrical. Okay. So these are the basic building block of the communication system. Here the important thing here is the we will cover is the transmitter, channel, receiver, and there is something called distortion and the noise. So when the signal is going through the channel, there are a lot of noise sources that comes into picture. Okay, and those noise sources will try to distort the our signal that we want to transmit and the receive. Okay, so we will analyze this noise and the distortion also in the syllabus. Okay. So these are the all the basic building block. Let me go to the next slide. Now let's come to the point why we need the modulation and the demodulation. So the modulation is needed because of multiple reasons. Okay. So one reason is the antenna size. Okay. So to radiate the signal through the antenna, that size of antenna should be the proportional to the wavelength of the antenna. Okay. So if we are talking about, let's say, the audio signal, and audio signal is generally in the range of 20 hertz to 20 kilohertz, and generally speaking, it will be somewhere around 3 kilohertz to 5 kilohertz. This it really goes to this lower and this high frequency range. Generally it will be like somewhere around 3 to 5 kilohertz. And for this kind of signal, if you want to radiate it through the antenna, the size of the antenna will be very high because the wavelength will be in order of kilometer. Okay. And since the wavelength is in order of kilometer, we need to design an antenna which will have a size in order of kilometer, and that is not possible. Okay, that will be very costly, and that doesn't make any sense. And because of that, we do a operation called modulation, and the purpose of this modulation is to transform this low frequency signal to a high frequency signal. Okay, so we have a signal which is a low frequency, which we will convert into the high frequency. So the high frequency can be like some hundreds of megahertz, or it can be in order of gigahertz also. So either it will be something like, let's say, 100 megahertz, or it can be in order of some tens of gigahertz also. Okay. So once we up convert this signal in the frequency domain, the effective so the lambda that we have for this modulated signal will go down. And since the lambda is down, we will need a smaller size of antenna to transmit this signal, or to we need to design an antenna which will be in order of this lambda, which is much lower than the unmodulated signal. Okay, so this is the first reason we want to do the modulation, is to reduce the size of the antenna. Second thing is the interference. So, for example, let's say we have a signal which is around 3 kilohertz. Okay, and someone has transmitted this signal into the wireless medium, let's say air. Okay, and then there is a one more person, and he is also transmitting, let's say, somewhere around 3 kilohertz signal into the air. These two signals will interfere with each other because they are transmitted to the same medium. Okay, but when it comes to modulation, what can be done is, for the first person, will up convert it to the some frequency, let's say f1, and for the second person we will use a different frequency, let's say f2. Okay, so let's say this f1 is 100 megahertz, and let's say this f2 is 105 megahertz. Okay, so now these two signal are at different frequency, so they will not interfere with each other. Okay, and because of that, we will be able to recover the signal without any interference, and two user can use the same channel. Okay, without worrying about the interference, because now both of them are using this different frequency. So that is one other motivation to use the modulation. So the first motivation is to reduce the antenna size. Second motivation is to reduce the interference of the different users. Anyone has any doubt here? Okay, let me go to the next slide. So let's see how does interference comes into picture. So let's say we have a 3 user, okay, and we have a single medium. So let's say we have a 3 user and we have a single medium. Let's say, let me call it as a air. This is the medium, wireless medium, and we have a 3 user X, Y, and Z. And all three want to use the same medium, and this is the spectrum of the 3 user. So the first user want to transmit this spectrum, second user want to transmit this spectrum, and third user want to transmit this spectrum. And since all three of them are using the same channel, they will transmit this spectrum into the same channel. Okay, once it comes to the same channel, effectively at this point GW, it is going to look like this: addition of all the three signal. Okay, so the first signal, this is the rectangular, this is the triangular, and then we have the kind of spherical. Okay, so when you all add all these three, it is how it is going to look like. Okay, now all three has interfered with each other. Now once you go to the receiver side and the user one tries to receive the signal, this x of omega, it won't be able to recover it, because this y of omega and z of omega has corrupted the x of omega because of the interference. And same is true for the user 2. User 2 want to receive the y of omega, but it can't recover the y of omega because of the interference with the x of omega x of omega and z of omega. And same story for the user 3. So this is the how the interference is not allowing us to recover the signal if we use the same medium for all the users. Now let's see how the modulation comes into picture and how helps us. So now when we have a three different user, we can assign the three different frequency for the three different user. So for the user X, I have assigned the frequency such that after the modulation or up conversion, it is somewhere here. For the second user, I have assigned the frequency such that after the up conversion, it is somewhere here. And for the third, it is somewhere here. Okay. So once you transmit the all three signal into the same medium, at this point, G of W is going to look like this. Okay. So this is the one signal, this is one signal, and this is another signal. Now, the user one is going to receive all the three of them. This circular, this rectangular, this triangular, all three of them. But all three of them are located at different frequency. So what user one can do is it can apply a band pass filter somewhere with centered around somewhere around this frequency and recover this triangular, and it will this band pass filter will reject this one and this one. So this two will not be allowed to reach the user one because of this band pass filter, and only this triangular one will go through the filter. So this one will pass through. Similarly, for the user 2, the band pass filter will look like this, and for the user 3, band pass filter will look like this. So this is how the interference is being removed with the help of the modulation. Let me go to the next slide. Now let's go to the analog modulation. How do we do that? So as we discussed, whenever we are doing the modulation, essentially we are up converting the signal from the low frequency domain to low frequency range to a high frequency range. Okay? So to convert the signal from low frequency range to high frequency range, we have something called carrier. Okay, and this carrier we call it as a cos omega ct or maybe sin omega ct. Okay, this carrier has a frequency of omega c, and this omega c is generally very high, and this we use to up convert the signal. Now there are two ways to up convert the signal. One we call it as amplitude modulation, one we call the angle modulation. Okay, in the case of amplitude modulation, the message is going to modulate the amplitude of the carrier. Okay, this is the carrier, and its amplitude is being modulated by the message. So this ET that you see here, it is a function of the message. In the case of angle modulation, the angle of the carrier is being modulated by the message. Okay, later on we will see that there are two types of this angle modulation. One is called phase and one is called frequency. That we will see later on. So first let's focus on this amplitude modulation. So in the case of amplitude modulation, we have a carrier whose amplitude is being modulated by the message, and that's why we call it as the amplitude modulation. Let's go through in detail. So for the amplitude modulated signal, this is how the signal generally looks. Xt is equal to a plus mt cos omega ct, where mt is a message and a is some constant. Okay, we'll see what is the significance of this constant. So this is how the amplitude modulated signal looks like. This is the carrier, this is the message, and this is the constant. And the carrier amplitude is a plus mt, which means that this a plus mt is a function of the message, and it is being modulated by the message. Okay. Now let's see how does the waveform looks like of this a plus mt cos omega ct. So for that, first I will assume that how the some generalized waveform of mt. So let's say we have a mt which looks like this. Okay, and a plus mt will look like this. Okay, so this is mt. Once you add a constant, all the entire this waveform will get shifted up, and this will become a plus mt. Okay, now this is a plus mt, which is being multiplied by the cos omega ct. Okay, so we are multiplying it with cos omega ct. So essentially the waveform will be kind of cos omega ct with varying amplitude, and amplitude will be decided by this a plus mt. So this is how the waveform is going to look like. So this is like a cos omega ct, but its amplitude is varying because a plus mt is a function of the message. So as the message is varying here, uh, a plus mt cos omega ct, its amplitude is also varying with the message. Okay? So this is how the waveform looks like. Okay, its amplitude is changing with the message. Now let's take a two scenario. First case is a plus mt is such that it is above the x-axis, and in second case a plus mt is such that there is some portion of the a plus mt which is below the x-axis. Okay. Now, when you plot these two cases, in the first case, it's you can trace this envelope here. This we call it as envelope, the dotted one that I have drawn here. This envelope is same as this signal a plus mt. Okay, and this envelope is never going to cross the zero. It is always being above this x-axis. In the second case, this envelope is crossing the zero and going to the negative side. Okay. Now, whenever we are in the second case, there is one problem, and this one we call it as a over modulation. And that the reason is because of the how we detect the signal at the receiver side. So once we do this modulation at the receiver side, we use some circuitry called the envelope detector. Okay. So envelope detector looks like this. You have a diode, you have a capacitor, and you have a resistor. Okay, this you can compare as a half-wave rectifier kind of circuit from the analog circuit design. So you will apply this modulated signal here to demodulate it, and this half-wave rectifier will try to demodulate it. Okay? So how does it? We know that this half-wave rectifier works only when the input signal is positive, and wherever the input signal is negative, it doesn't work. Okay. Now, in the first case, our envelope is never going to be negative, and that's why this half-wave rectifier will work perfectly. But in the second case, the envelope of the signal is going negative, and that's where this half-wave rectifier will not work. Okay. So in the first case, envelope detector will simply detect the envelope like this. But in the second case, if it tries to detect the envelope, it will detect correctly till this point, but after this point it will become zero. Okay, and that is the problem here, that we are not able to get back to our original message. Our original message was not zero. Here we are getting flat here. Okay, so we
But
want, yeah.
actually, in the third diagram, I didn't find the difference. Actually, I mean, I didn't got the point of that. Actually,
Okay, okay. Let me explain it. So this analog detector works like this. So let's say initially we are starting, we are applying this signal, and since this is positive, this is half-wave rectifier kind of circuit, it will work like, it will charge like this. It will charge the capacitor, and it will reach the peak point. Okay. So at this point, our signal output signal at this output of this analog detector is same as whatever we have applied at the input. Now, from this point onwards, once it has reached the peak, the input signal is going down rapidly. You see it's going down very fast. But this cap is not going to lose its charge very quickly, because cap is known for uh, to not to change its voltage very quickly. Okay, and this cap value is generally pretty high, and that's why this voltage across this cap is not going to change very quickly. So what happens that for this diode, the negative side is going down rapidly because the input is going down rapidly, but positive side doesn't change much. And because of that, what will happen that this diode will become reverse bias. Okay, since the diode is now reverse bias, this diode will become off, and this capacitor will slowly discharge through this resistor. So this circuitry is kind of off, and you have just this capacitor and this resistor, and this capacitor will slowly discharge through this resistor. So you can say that it is slowly discharging like this. Okay, and again it will hit the message, and again it will charge. So once it reaches this point, just at this point, what will happen that your input signal is more than what the voltage across this capacitor, and again it will charge slightly here, and again it will discharge, Once input goes down rapidly and charge, discharge, like that it will continue. Okay.
Okay.
If you see the importance of the signal being positive, right? Whenever, so if the signal is, this envelope is going to the negative side, we will not be able to recover. We are able to recover the message approximately, because here, if you see the, it is tracking the envelope. So this is the envelope here, a plus empty, and we have plotted a plus empty cos omega ct here. And after that demodulator, we are kind of trying to go back to this a plus empty. Okay. So at the output, it will be kind of approximately a plus mt, and it will happen only when the envelope of the signal is positive. If the envelope of the signal goes to negative, it will detect the envelope correctly till this point, but here onwards, it will detect like this envelope. Instead of going down, which is the our exact signal, it will try to go up, because this is the direction which we have the positive value. Okay. So instead of tracing this envelope, it will trace like this. Okay. And this is the wrong value. We want it to go down because our original signal was going down. Okay. So that is the difference between these two. Now is it clear?
Oh, yes, yes, yes.
Okay.
Direction changed in between, right?
Yeah, correct, correct.
Okay, okay,
Because
okay.
yeah, because this envelope you see, it is going negative side. Okay, and because of that, here envelope should go down after the output of the half wave rectifier, but it is not capable of doing those kind of tracking, because it is capable of tracking the signal only when the signal is positive or envelope is positive.
Okay, okay.
So here there is one criteria that this envelope has to be always positive. That means that a plus mt has to be always greater than or equal to 0. Okay. So if the
Okay.
signal is satisfying or envelope is satisfying this criteria, then we will be able to use this envelope detector to recover the signal. Otherwise, we will not be able to use the envelope detector. Okay. So here there is a one term called modulation index, and that is equal to MP by A, where A is this constant that we have written here, and MP is the maximum value of the message, or you can say minimum value of the message. Here I am assuming that maximum and the minimum has the same magnitude. Okay. So its maximum value is MP and minimum value is minus MP. So the modulation index will be given as MP by A, where MP is the, or you can say MP is the mod of the minimum value. Okay. MP is equal to mod of the M minimum. Okay. So this we call it as a modulation index, and just now we covered that A plus MT has to be greater than or equal to 0. Now the worst case will happen when MT is at the minimum value. So when MT is the minimum is at minimum value, we want this A plus MT to be positive. So we can say that A minus MT should be greater than 0 or equal to greater than 0, or A should be greater than equal to MP. Okay. Or you can say that MP by A should be less than or equal to 1. Okay. So it means that this is the modulation index MP by A, which is equal to mu here, and this mu should be less than 1. Okay. So modulation index should be less than or equal to 1 and greater than 0. This greater than 0 is coming because it always has to be some positive number, this MP by A, and that's why it's just greater than 0. So modulation index should always be greater than 0 but less than equal to 1. When modulation index is greater than 1, we call it as a over modulation, and that is the case when our envelope is satisfying this criteria for some point. Okay, and that we call it as over modulation. And if there is a over modulation, envelope tracker will not work properly. We will not be able to go back to our original signal. Anyone has any doubt? Let me go to the next slide. Okay. So yeah, I will just quickly cover the how this rectifier detector works. Just now I have covered it. I will just show it clearly now. So generally this cos omega ct, right? This omega c is very high And because of that, the frequency of this cos is very high. Okay. So when you plot the A plus MT cos omega CT, okay, it is going to kind of look like this. Okay. Let's say you have this kind of envelope. So it is going to look like this. Since this cos omega CT is very high, you will kind of see very dense signal here. In the last slide, I drew very sparse kind of signal, but it is going to be very dense like this, okay? Because cos omega CT is very high, it will change very rapidly. So once you apply the signal to this half-wave rectifier, so initially it will track the message, and then once it reaches the peak value, there is a cap here actually, okay? The input is going down very rapidly, so the potential at this point will be kind of very going down very rapidly, but because of this cap, it will hold the voltage here, and it will slowly discharge through this resistor, and then again it will go up and go down, so like this. So this, because this cos omega it is very high, it is kind of very closely able to trace the envelope. That's why we call it as an envelope detector. Okay. Now once we get this envelope is kind of A plus MT, okay? And we want to recover MT, we want to remove this A. So we use this cap here. We know that cap will block the DC, and this A is kind of DC signal. Okay, this is DC. And so what we do, we pass it through the cap here. And once we pass it through the cap, this cap will block this DC, and you will get the MT across this resistor. Okay. And the purpose of this low pass filter is to remove all these glitches. So you will see that it is going down and going up and then going down. It will be kind of this kind of signal. Okay. It is trying to press the analog. So you see there is a glitches here. So this low pass filter will try to remove those glitches. So it will kind of trying to smooth the signal. Okay. It will make it kind of slowly varying instead of this sharply changing. Okay. So that is the purpose of the low pass filter, is to make this kind of a smoother, and the purpose of this capacitor is to remove the DC. Let me go to the next slide. Yeah. So if you select back, we discussed about the modulation index, which I wrote it as a MP by A, where MP is the mod of minimum value of the signal. Okay, and here we have assumed that the maximum value of the signal and the minimum value of the signal has the same magnitude. Okay, but in general it might not be the case. Let's say m max is not equal to minus of m minimum. In those cases we should use this as a formula. So in those cases the modulation index will be given as m max minus m minimum divided by 2a m max plus m minimum. Okay, in the case when m max is equal to minus m minimum, okay, this formula will simply become this. You can check it, and this whole thing will become 0 because ms is equal to minus m minimum, so this will become 0, and you will be left with 2a here in denominator, and numerator you can directly write it as a 2 into m max or m min mod. Okay. So this will finally transform to this value. So this is the generalized formula for the modulation index, m max minus m minimum divided by 2a m max plus m min. Now let's go through one problem. So let's say we have a signal mt equal to 2 cos omega 2 pi fmt, and we have a carrier. So this is the massive signal, this is the carrier signal, and we need to find out which of this four option has a correct AM signal without any kind of over modulation. So we need to find out the signal for which the envelope is never negative, or you can say A plus MT was always positive. Okay, we just need to find those cases. So if you see the first signal, which is AC plus MT, so this is AC plus AC into MT, not plus, and MT is this 2 cos 2 phi FMT. So AC 2 cos 2 pi FMT, and this is the envelope. Okay, and we know that this envelope will be both positive and negative, and since this envelope is going to be negative, it will have the over modulation. So this is not satisfying this criteria. Okay. Let's take the second case. It has the envelope which is equal to AC into 1 plus MT. Okay, so in this case, you can say that it is AC 1 plus mt is given as 2 cos 2 pi fmt. Again, in this case, this term 1 plus 2 cos 2 pi fmt, it is going to be negative value for some time. Okay, for some time it is going to be negative, sometime it will be positive, because this cos will have minimum value of -1. Okay, then you have 2, so it will become -2, and you have +1, so it can go to -1. Because of that, we can say that it has a over modulation. The third option we have is AC plus cos 2 pi fct, 1 by 4 AC mt cos 2 pi fct. So let's take the cos 2 pi fct common, and that will, after taking the common, we will get the envelope as a AC plus 1 by 4 AC into mt. Okay, you can write it as AC plus 1 by 4 AC, and mt you can write it as a 2 cos omega mt. I am writing omega mt, but omega mt is equal to 2 pi fmt. And this will cancel out, it will become 1 by 2. So this is AC plus AC by 2 cos omega mt. Now in this case, this will always be positive, because this cos omega mt will have the minimum value equal to -1. Okay, so it will become minus AC by 2, but we have a plus AC also here, and which will make sure that this total term never goes to below 0. Okay, or never goes to negative value. So this is the correct option, which doesn't have any kind of over modulation. If you see the third option, it is not even the AM signal. Okay, because it has some weird expression. AM signal should always be in the form of A plus mt cos omega ct, or it can be the form of something like A into 1 plus K into mt cos omega ct. It can be in this form also, because both are similar. Anyone has any doubt here? Let me go to the next slide. Okay. Next is about the power efficiency. So the power efficiency is given as the power that we are using in the message term divided by the total power. Okay. So the power that we are using in the message term, we call it as a useful power divided by total power. Total power is the carrier power plus the useful power. Okay. So if you see this AM signal, it has a this term A cos omega ct. We call it as a carrier term. Okay, and this we call it as a message term or useful term. Okay, because this is the term which contains the message. This term doesn't contain the message. Okay, now the carrier power, you can simply write it as a square by 2, because we know that from signal system that the power of this signal will be a square by 2. For the mt cos omega ct, you can write it as a m square. This is actually the mean square value divided by 2. Okay, so the efficiency will be given as useful power, which is this term, mean square value by 2, divided by total power, which is the carrier power plus this useful power. Okay. So once you put this PC and PM here, this is the expression we are going to get. Okay. So this is the efficiency of the AM signal. Now let's take a special case when our message MT is a kind of sinusoidal signal. So let's say our message is sinusoidal signal. So it will become AM cos omega MT. Now the power of the signal will be given as AM square by 2. Okay. Let's put it here and let's see what we get. So once you put it here and rearrange everything, you'll get AM square divided by AM square plus 2A square. Okay. Now we know that for this signal, mu will be equal to AM by A. Correct? AM is the maximum value of the signal, or you can say the magnitude of the minimum value of the signal, and divided by A. Okay. Now, if you take this expression and divide both numerator and denominator by A square, divide both numerator and denominator by A square, you see the numerator will become mu square and denominator will become mu square plus 2. Okay, so this is also a formula for the efficiency. Now if you see this efficiency, We know that this mu is always in this range, and the maximum value of the mu will be equal to 1. Okay, since the maximum value of the mu is equal to 1, that gives us the maximum value of the efficiency, which is equal to 1 by 3. Once you put mu equal to 1 here, it will give us the efficiency, which is equal to 1 by 3. Okay, so in the case of amplitude modulation, the efficiency of the modulation is 33.33%. So this is the case only when mu max is mu is equal to 1. If mu is less than 1, it will definitely be less than 1 by 3. Okay. Let me go to the next slide. So let's take a problem. We have a signal, message signal, which is given by this formula, and it is modulating the carrier omega c, cos omega ct, and the modulated signal is given by this formula. We need to find out what will be the efficiency. Okay. So in this case, when you try to find out the efficiency, we need to find out eta, which is equal to message power content which has the message power divided by total, which is the message power plus carrier power, or you can say mean square value of the message divided by mean square value of the message plus a square. Okay, now in this case you see a is equal to 1, so you can say it is 1 plus. Now what is the mean square value? So mean square value will be given as 0.5 square by 2 plus 0.5 square by 2. Okay, we know that root mean square value will be like this, but we want to find out just the mean square value, so just remove this root here. Okay. So the mean square value will be 0.5 square by 2 plus 0.5 square by 2, or you can say simply 0.5 square, which is equal to 0.25. So it is equal to 0.25 plus 0.25, or you can say that 0.25 divided by 1.25, which is equal to 1 by 5, or 0.2, or you can say 20%. Okay, so here this is the power efficiency that we are getting. Now there is a one common mistake that people do here is they, instead of using this eta formula, like this formula, they use this formula. Eta is equal to mu square divided by mu square by 2. Now this formula you should use only when your message is just a single sinusoid, which is something like this. Okay, so if message is in this form, then only we should use this formula. Okay, because we derived this formula by assuming that message is this. But if message is not this, in that case, we should use the general formula, which is this one. Okay, so if you use this formula, you not get the 20% here, you'll get a 33% actually. So because in this case, if you see the maximum value of this or the minimum value of this message is equal to minus 0.5, sorry, not minus 0.5, minus 1. Okay. The maximum value will be plus 1 and the minimum value will be minus 1. And since this is minimum and maximum value, your mu will be equal to 1 by 1, because A is 1, MP is also 1. So this will give us mu equal to 1. Once you put mu equal to 1 here, you'll get that 30% of the efficiency. But we know that from this one, we are getting 22%. So if you use this formula, this will be the wrong answer, because you should use this formula only when we have a message which is in this sinusoidal form. Let me go to the next slide. Okay. Now, this is one of the IES problem, previous year IES problem. So we have an amplitude modulated signal which is given by this. Okay. Here, omega m is the, actually this is actually multiplied here. Somehow it has come here. So this is, and this one are multiplication. Now this omega m is the message frequency and omega c is the carrier frequency. We need to find out what is the power efficiency here. Okay. Now in this case, you can directly use this formula that eta is equal to mu square divided by 2 plus mu square. Because in this case, if you see the modulated signal, our message is in the form of the sinusoid, a single sinusoid. So we can directly use this formula. So mu will be equal to what is the maximum or minimum value of the signal, which is 0.5a divided by this constant a, and this will give us the 0.5. Okay, so this is the mu modulation index. Let's put this mu here. Okay, so we will get this thing, okay, which will be equal to 1 by 9, or you can say 11%, 11.11%. Okay, so this will be the correct answer. Anyone has any doubt here? Okay, let me go to the next slide. Now, what is the ratio of the modulating power to the total power of 100% AM modulation? Okay, so in this case, when it says that it has 100% AM modulation, that means that mu is equal to 1. Okay, that's what it means by 100% modulation. If it says that it is 80% AM modulation, it means that mu is equal to 0.8. Okay, and so on. So in this case, it is saying the 100% AM modulation. That means that mu is equal to 1. And we know that when mu is equal to 1, the ratio will be 1 by 3. Okay, 1 ratio 3. So this is the modulating power divided by total power. So we have derived the this derivation that eta should always be less than equal to 1 by 3. And since here it is asking about 100%, in that case mu will be equal to 1 and you will get eta equal to 1 by 3. Okay, so this is the ratio of the modulating power to total power. Let me go to the next slide. Okay. Now in this problem, it is kind of framed in a very weird way. So we have a current in the AM transmitter equal to 18 ampere when there is no modulation. When it says it is unmodulated, it means that the message is not present. Message is 0. Okay. So you have just A cos omega ct. You don't have empty cos omega ct term. Okay. So in that case, you have a current which is equal to 18 ampere. But when you do the modulation, the current increases to 20 ampere. So for MT plus A cos omega ct, for this complete term, the current is 20 ampere. Okay. Now we need to find out what will be the efficiency. Okay. So this is the carrier term and this is consuming the 80 ampere current. So its power will be kind of 18 square by R, and let me assume the R equal to 1. So in that case it will become 18 square and that is 324. Okay. In the second case we have MT plus A. In that case the power will be 20 square, which is equal to 400. Okay. So this is the carrier power and this is the carrier plus message power. Okay. Now our efficiency is given as message power divided by total power, which is carrier plus message. Now to find out the message power, we can use these two equations. In the first equation, we have the carrier power. In the second equation, we have the carrier plus message power. When you subtract this two, you will get the message power. So PM will be equal to 76, right? When you subtract this two, you'll get the PM and PM is equal to 76. So efficiency will be equal to 76 divided by total power, which is equal to 400. Okay. Now this A will be equal to mu square divided by 2 plus mu square. Okay. Now when we solve this, we'll get the value of the mu. Okay. After the solution, we'll get the value of the mu, and that will be the 0.68. Okay. So this is how we have to approach this problem. And here, one mistake that people commonly make here is, instead of doing this square here, they directly treat this 80 ampere as a power and they write it like this: PC is equal to 18 and PC plus PM equal to 20. So don't make this mistake. The power will be equal to current squared by R, and here R you can assume to be 1, and that will not make any difference. Anyone has any doubt here? Let me go to the next slide. Now let's see how the spectrum of the amplitude modulation looks like. So when you see the time domain signal, it looks like A plus MT cos omega ct, or you can write it as A cos omega ct plus MT cos omega ct. Okay. So before drawing the spectrum of the AM signal, let's first assume that we have a message and it has some kind of a spectrum. So let's assume that we have a message and the spectrum looks like this. Okay. And from there, we will try to find out what will be the spectrum of the modulated signal. Now, the first term that we have here is A cos omega ct. Okay. Now, when it take the Fourier transform of this A cos omega ct, we know that the Fourier transform of the cos omega ct will be two impulse, one located at fc or minus fc or minus omega c, and second one located at plus fc or plus omega c. Okay. So that Fourier transform of A cos omega ct will be two impulse. Now, what will be the Fourier transform of mt into cos omega ct? Okay. So this you can write it as a mt e to power j omega ct plus e to power minus j omega ct divided by 2. Now you are multiplying mt with e to power j omega ct in the time domain. So in the frequency domain, it will be frequency shift. Okay, so this you will get, and for this second one, this one you will get. Okay. So this is the spectrum in for the second term, and this is the spectrum for the first term. Okay. Now let's plot this. How does it looks like? So first we have a two impulse located at fc and minus fc. So these two are the impulse. Now other than these two impulse, we have the shifted version of the MF. One is shifted by fc, one is shifted by minus fc. So when you take this MF and shift it by fc, this is how it is going to look like. And when you take this MF and shift it left by fc, this is how it is going to look like. Okay. Now, if you see this signal, the unmodulated signal has a bandwidth which is equal to p. Okay. But when you do the modulation, this is the bandwidth and this is equal to 2b. Okay. So how do we define the bandwidth? Bandwidth is you just take the positive frequency and calculate the range of the frequency over which the signal is non-zero. And that we call it as a bandwidth. Here in this is B. For the second signal, which is the modulated one, the range over which the signal is non-zero is from fc minus b to fc plus b. And if you take this range, it is equal to 2b. Okay. So the bandwidth of the unmodulated signal is b, but for the modulated signal, it is equal to 2b. Okay. So the bandwidth gets double when you do this amplitude modulation. Okay. Now, if you see this signal, we have a two lobe here. One is below this fc, and after this minus fc. Okay, this thing. Let me just draw it again. Okay. So one is you just draw this rectangle from minus fc to fc. Whatever is inside this rectangle, we call it as a lower sideband, and whatever is outside this rectangle, we call it as a upper sideband. Okay. So this complete thing is known as a sideband. This is a one sideband, this is another sideband, this is also a sideband, and this is also a sideband. Okay. So we have the upper sideband and the lower sideband. Upper sideband is a thing which is outside this rectangular, and the lower sideband is a portion of the spectrum which is inside the rectangular. Okay. Now we know that the mass. Let's assume the message power is PM. Okay. So the message power is actually the power of this triangle plus this triangle, and carrier power is, which is PC, is the power of this impulse and plus power of this impulse. Okay. Now here we have a message power which is equal to PM. So the power in the lower sideband will be equal to Pm by 2, and power in the upper sideband will be equal to Pm by 2. Because, and after it, once you add this 2, that will give you the total message power. Because since in the frequency domain, message is kind of divided into two parts. One is the upper sideband, one is the lower sideband. And that's why you can say that upper sideband contain the half of the power and the lower sideband contain the half of the power. Okay. So anything which is inside this rectangular, okay, this rectangular from minus fc to plus fc, that contain the power of Pm by 2, and anything outside this rectangular that contain the power equal to another Pm by 2. I have not included this to impulse. Impulse power is separated, so that is equal to P's. Anyone has any doubt here? Okay, we'll go to the next slide. Now let's see how to solve this problem. So we have been given an AM signal and its bandwidth is 20 kilohertz. Okay. So when I say we have been given an AM signal and its bandwidth is 20 kilohertz, so we are talking about this bandwidth from this point to this point. Yeah. So let's assume that our message spectrum looks like this. So after the modulation, it is going to look like this. Okay. This is centered at FC. This is centered at minus FC. Now this bandwidth is given as 20 kilohertz. Okay. Now it is saying that the highest frequency component of this AM signal is present at 800 kilohertz. That means that we are talking about this point because this is the highest frequency content and it is at 800 kilohertz. Now we need to find out what should be the carrier frequency. Okay. So here you should know how does everything look, this spectrum looks like. So this width is 20 kilohertz. This point is 800. So this point will be 780. Now your FC will be somewhere in the middle here. So this is 780, this is 800. So the middle of this two will be 790 kilohertz. Okay. So the carrier frequency of the signal will be equal to 790 kilohertz. Anyone has any doubt here? We'll take 2-minute break and then we will continue. Okay, this is another problem. So AM signal with a carrier of 1 kilowatt has, so this is the carrier power. Carrier is 1 kilowatt and 200 watt in each side band. Okay, and we need to find out what is the percentage of modulation. So when it asks for the percentage of modulation, that means that it is asking for the modulation index. Okay, mu. Now first, so we will use this formula that efficiency is equal to mu square divided by 2 plus mu square. So for that we need to find out what is the efficiency. So first thing is that carrier power is given and it is written that each side band has the 200 watt. So that means that upper side band has the 200 watt as well as the lower side band has the 200 watt. So your message power will become 400 watt. Okay, and then the carrier is 1 kilowatt. So the efficiency will be equal to 400 divided by 1000 plus 400. Okay, which will give you the 4 divided by 40 or 2 divided by 7. Okay, so this is the efficiency which is equal to mu square divided by 2 plus mu square. Okay, this one you can also write it as a 7 by 2, just reverse it, 1 plus 2 divided by mu square. Okay, so once you subtract this, so this is like equal to 3.5 minus 1 equal to 2 by mu square, and then you can write it as a mu square is equal to 2 by 2.5 or 4 divided by 5. Okay, and you can solve this, but and once you solve it, it will turn out to be 89.4. Okay, so this will be the percentage of the modulation. So the modulation index is also known as a percentage of the modulation. Okay, next slide. Now let's see how do we remove the carrier and what is the benefit out of it. So when you take the AM signal and remove the carrier portion of it, okay, which is equal to A plus A cos omega ct, you will get just empty cos omega ct. Okay, so this we call it as a double sideband suppressed carrier. We call it a suppressed carrier because you have removed the carrier term, which was A cos omega ct. Okay, this we have removed, and after removing this, we got just x equal to empty cos omega ct. Okay, now in this case, if you calculate the efficiency, you will get 100% efficiency. Eta will always be equal to 100. Okay, the reason is that the total power is same as the power of the message term, because here we have only the message term here. Okay, so here the efficiency will always be equal to 1, or you can say 100%. Now let's see the spectrum. So this spectrum will be similar to what we have seen for the AM signal. Only different is that we will not see the two impulse that was located at minus fc and the plus fc, because those impulse correspond to the carrier term and we don't have the carrier term here. Okay, since we have removed the carrier term, we will have just the upper sideband and the lower sideband term. Okay, now again in this case also, if your message bandwidth is B, your modulated signal bandwidth will be 2T. Okay, because it is ranging from fc minus B to fc plus B. Okay. So whether you do the amplitude modulation or double sideband suppressed carrier modulation, both of them has the same bandwidth. But the difference between DSBSC and AM is that the power efficiency of the DSBSC is always 100%. On the other hand, the power efficiency of the amplitude modulation is at max. It can go up to the 33%. Okay. Now let's see how do we demodulate this. Okay. So demodulation of this DSBS is very straightforward, and that is that you just take this modulated signal, which is empty cos omega ct, and multiply it with cos omega ct. Okay, so once you multiply this two, at the output of this multiplier, you will get empty cos square omega ct. Okay, now we know this formula that cos 2 theta is equal to 2 cos square theta minus 1, or you can say that cos square theta is equal to 1 plus cos 2 theta by 2. Okay, I will use this formula and write this cos square omega ct like this. So empty 1 plus cos 2 omega ct by 2. Okay, so if you see this complete thing, we have an empty by 2 and we have empty cos 2 omega ct by 2. Okay, now empty is a kind of low frequency signal, so empty by 2 will also be low frequency signal, but this empty multiplied by cos 2 omega ct will be high frequency signal. So once you part this complete thing through a low pass filter, at the output you will just see the empty by 2. This second term will get filtered out by this low pass filter. Okay, so this is the how the demodulation works for the DSPSC. We don't use envelope detector here. Envelope detector will not work because we don't have this amplitude to be always positive. Now here there is one problem is that the phase of this cos omega ct and the phase of this cos omega ct has to be same to get the signal back. Okay, if they are different, then also we can get the signal back, but there is some problem. And if they are apart by 90 degree, like this is a cos and this is a cos omega ct plus 90 degree, that you can say that sine omega ct, because sine and cos is 90 degree shifted version of each other. If the input signal and this cos omega ct are 90 degree apart in phase, in that case you will never be able to recover your message signal. Okay, so that is one of the problem that we have for the DSBC demodulation. In the case of amplitude modulation, you don't have to face this kind of synchronicity problem where the input and this cos omega ct has to be in same phase. In the case of AM, you don't have to worry about this phases thing. But in the case of DSBC demodulation, you have to take care of these phases. If the phases is not a lot of degree different between these two, then in that case it will create a problem. Okay, so that is the main difference between the AM and DSBSC. In DSBSC, we have very good efficiency, but that is coming at the cost of this synchronicity problem. Okay, that is a trade-off that we have to do here. Okay. Now let's see what happens if they are not in phase with each other. So let's say this input signal is empty cos omega ct, but this signal, instead of cos omega ct, it is cos omega ct plus theta. Okay. So at the output of this multiplier, you'll get empty cos omega ct into cos omega ct plus theta. Okay. This is the term you will get. Now here you can apply the cos A into cos B formula. Okay. Once you apply this cos A into cos B formula, it is how it is going to look like. So mt by 2 cos omega ct oh, wait. Yeah. So you'll get cos omega ct plus theta minus omega ct, cos A minus B, and there will be minus cos A plus B term. Okay, minus cos A plus B term, but minus cos A plus B term will get filtered out by this low pass filter. Okay, now if there is a phase, right, this theta, instead of getting just empty by 2, you get empty by 2 into cos theta. This cos theta is coming as a extra term when there is a phase difference between the this cos and this cos. Okay, and if this theta, the phase difference is pi by 2, we know that when this theta is pi by 2, it will become cos pi by 2, and this complete thing will become 0. So you'll not get anything at the output of this low pass filter. So that's the problem that we have here. If you have more and more phase difference between this input and this cos omega ct, you will reduce the strength of the recovered signal more and more. If this theta goes up, so if this theta is 0, they're perfectly synchronized. You'll just get empty by 2. But if theta goes up, your strength of the signal goes down, and at theta equal to pi by 2, your signal strength will be 0. Anyone has any doubt here? Let me go to the next slide there. Now the DSB-SC demodulation circuit, in the frequency domain, how does it looks like? Let's see. So this is the modulated signal, and this modulated signal we are multiplying it with cos omega ct. So we know that when you multiply the signal with cos omega ct, what it does is it takes the signal and shift it left and right by fc. Okay, so you take this spectrum, this modulated spectrum, and shift it left and right by fc because you are multiplying it with cos omega ct. So when you shift it left and right by fc, so take this, shift it left, you get this one. And take this, shift it left, you'll get something like this here. Okay. Now, when you shift it right, you will take this.
Hello.